Hey everybody, welcome to another calculus lecture. Last time, if you remember, that we talked about what the tangent to the graph of a function was, or the line tangent to the graph of the function, or the tangent line to the graph of the function. That we talked about that. And the tangent or the tangent line to a function at a particular point x1, f of x1, is a line that contains that point and has the same exact slope as the graph of the function at this point. So right at this point, x of 1, f of x of 1, the slope of the tangent line and the slope of the graph of f of x are exactly the same. And we discussed strategies for computing the slope of the tangent because for some reason or other, knowing the slope of the tangent at any point on the graph of a function is an important thing. We don't know why that's important yet, but it turns out to be important. And so we set about trying to find ways to compute the slope of a tangent line to the graph of a function. And our first attempt, we ran into a brick wall. We thought, let's just use the slope formula. y2 minus y1 over, let's see, let me do it this way. No, this way. y2 minus y1 over x2 minus x1. Just use the slope formula. And then we realized, well, in order to use that formula, we have to know the coordinates of two distinct points on the graph of that function. And you know what? We only know one point. Let me say that again. In order to use the slope formula, we have to know the coordinates of two distinct points on the line that's tangent to the graph of the function. We want to find the slope of this line. And in order to compute the slope of a line, we need to know 2 points. We don't know 2 points on this line. We only know one, x of 1, f of x of 1. So that seemed like a good plan, but it fell by the wayside because we couldn't find 2 distinct points on this tangent line. So we went to plan B, as we often do in mathematics. And here's plan B, just as a refresher. Given the graph of f of x and a point, x of 1, f of x of 1 on the graph of f of x, here's what we do. Pick a point, x of 2, to the right of x of 1 on the x-axis. And we did that. Here's the point, x of 2, to the right of x of 1 on the x-axis. We picked a point, x of 2. Second, it says plot the point, x of 2, f of x of 2 on the graph of f of x. And we can do that. We can find f of x of 2. All we have to do is take x of 2 and plug it into f of x. So we plotted the point, x of 2, f of x of 2 on the graph of f of x. And then the third thing we did, we constructed a secant. We constructed a secant joining the point x of 1, f of x of 1 to the point x of 2, f of x of 2. So here's the secant that connects the point x of 1, f of x of 1 to the point x of 2, f of x of 2. Now, why did we do that? Number 4 says we'll use the slope of the secant to approximate the slope of the tangent. We want the slope of this line, the slope of the tangent, but we don't know how to get it. So what we'll do is we'll take the slope of this thing, the secant, which we can compute, and we'll use the slope of this secant as an approximation to the slope of the tangent. So the slope of the tangent, m sub tan, is approximately equal to the slope of the secant, m sub SEC, and it's just the slope formula, y2 minus y1 over x2 minus x1. Change in y over change in x. So y2 minus y1 over x2 minus x1. That's our plan. And now we're caught up to speed on what we had been doing in the last class. In order to go further, it's going to be beneficial for me to reformulate what I've done. So let me put up the preliminaries on the board. Okay, here's the reformulation that I need to begin. And it involves something called delta x. If any of you have had chemistry before, then you've worked with the delta notation. For example, delta capital T, you recognize that as being change in temperature. Or maybe delta P, change in pressure. Or perhaps delta V, change in volume. So if you've had some chemistry, you're probably familiar with the delta notation. We use the delta notation in a similar fashion in math. And here we're going to define delta x, which we denote this way. In this triangle, that's the Greek letter delta. So this is delta x. And delta x represents the change in the value of the variable x. So delta x is the change in x. And just as an example, if x sub 1 is the initial value of x, and x sub 2 is the final value of x, then the change in x is going to be the final value minus the initial value, x sub 2 minus x sub 1. And so we'll be using this relationship quite a bit. Delta x equals x2 minus x1. And now I want to point out what happens if we manipulate this equation. Suppose that we add x sub 1 to both sides of the equation. So we have x sub 1 plus delta x equals x sub 2. Or if we put the x sub 2 on the right, we have x sub 2 equals x sub 1 plus delta x. We're going to be using this relationship involving delta x, and we'll be using this relationship also. Before we get back to our tangent line problem, I do want to make a few more comments about delta x, especially for the sake of those of us who may not be used to using this notation. Okay, just a few remarks about delta x for those of us that may not have much experience working with the delta notation. Delta x is a variable just like x, y, and z are variables. So this is just another name for a variable. And this is an important point. Delta x is not delta times x. When we look at this, we do not want to look at it as delta times x. That's not what it is. Delta x is not the product of two different symbols. Delta x is one symbol. So this is not two symbols multiplied together. Delta x is one symbol representing one variable. And therefore, since delta x is just one indivisible symbol, we cannot do this. We cannot say, oh, delta x divided by x, the x's cancel, and we just get delta. We cannot do this. We do not view this as delta times x. So if we have, let's say, delta x over x, we can't cancel the x's. This is not delta times x, so we can't cancel the x's. Delta x is just one symbol representing one variable. So look at this just like you'd look like y or z or any other variable. Okay, I've said enough about delta x. Let's get back to our tangent problem. Okay, back to where we were yesterday. Here's the tangent line, or the line tangent to the graph of the function of f of x. We want to know the slope of this tangent line. The only problem is we only know one point on the tangent line. So we've constructed a secant that we picked a point x of 2 to the right of x of 1 and plotted the corresponding point on the graph of f of x, x of 2, f of x of 2, and we used the point of tangency, x of 1, f of x of 1, and this point, x of 2, f of x of 2, to construct a secant. And we reasoned we can use the slope of this secant to approximate the slope of the tangent. And that's still our plan B. So we're going to have the slope of the tangent being approximately equal to the slope of the secant. And before I compute the slope of the secant, I'm going to reformulate this in terms of delta x. So remember, x of 2 is equal to delta. Let's see, what is x of 2? X of 2, which is what we have here, is equal to x of 1 plus delta x. So we just renamed this point. It was x of 2. Now we're going to represent it as x of 1 plus delta x. The two are equivalent. X of 2, x of 1 plus delta x, same thing. Well, if I replaced x of 2 with x of 1 plus delta x down here, I'm going to have to do the same thing up here. So this point is going to be renamed x of 1 plus delta x, and then f evaluated at x of 1 plus delta x there. Now we've just reformulated everything in terms of x of 1 and delta x. We took x of 2 and expressed it in equivalent form, x of 1 plus delta x. And just one other thing. What's the distance from x of 1 to x of 1 plus delta x on the x-axis? Isn't it just delta x? So this distance, the horizontal distance between the points of the secant, is delta x. Now with this set of notation, I will attempt to approximate the slope of the tangent. And so I have slope of the tangent, m sub tan, is approximately equal to the slope of the secant, m sub sec, and we just use the slope formula. y2 minus y1 over x2 minus x1. So that's y2 f of x sub 1 plus delta x. There's our y2 minus y1 f of x sub 1 all over x2 x sub 1 plus delta x minus x1, x2 minus x1, which is x sub 1. And that's equal to f of x sub 1 plus delta x minus f of x sub 1. And in the denominator, whoops, what should this have been? Let me clear this up first. Here's x sub 2, x sub 1 plus delta x, and we subtract x sub 1. X sub 1, there. This is going to make all the difference in the world. When I simplify the denominator, the x sub 1's wipe each other out, right? And so I have just delta x on the bottom, where delta x is the distance from x sub 1 to x sub 1 plus delta x. So let me just encapsulate that as a result. The slope of the tangent is approximately equal to the slope of the secant, and that is f of x sub 1 plus delta x minus f of x sub 1 all over delta x. So we have an approximation for the slope of the tangent, which is what we set out to do. But I'm kind of worried. I'm kind of worried because I want the slope of this line to be a good approximation to the slope of that line. And if the slope of two lines are approximately equal, that means that they're pretty much parallel, right? Parallel lines have the same slope. So if the slope of one line is a good approximation to the slope of the other, the two lines should be very close to being parallel. And I look at what I have here and I'm bothered because the secant and the tangent are not close to being parallel. The slope of the secant doesn't really appear to be a good approximation to the slope of the tangent. Now, they're both going uphill from left to right, so they're both positive. But other than that, it doesn't look like the slope of the secant is going to be a good approximation to the slope of the tangent. And so that's disheartening. And I look back at how I set this up, and I'm asking myself, how could I have set this up differently so that the slope of the secant would be a better approximation to the slope of the tangent? Or to put it another way, how could I have set this up differently so that this line is a lot more close to being parallel to this line? What could I have done differently? And there are probably two different answers that you could give to this, and they're equivalent. Some of you are probably looking at this and saying, hey, here's the end point of the secant. Why the heck did you put it all the way out here? Why didn't you pick some point on the graph, like right here, that's a lot closer to the point of tangency? Why didn't you pick some point right about here to be the other end point of the secant? Some others of you are saying, well, maybe we can just take this point right here and slide it along the graph so that it's closer to the point of tangency. And I like both of those explanations. I could have chosen this point to be a lot closer to the point of tangency. And you know what? That would mean that this point was going to be my x of 1 plus delta x, and f of x of 1 plus delta x. And I'm going to have a new secant. Oh, by the way, I'll talk about that later. I'm going to take the end point of the secant and move it along the graph so that it's closer to the point of tangency. And so here's my new secant. And sure enough, the slope of the secant is going to be a much better approximation to the slope of the tangent. I just took the end point of the secant, which was right here, and moved it along the graph closer to the point of tangency. And notice something else that happened as a consequence of that. Is I moved the end point of the secant closer to the point of tangency. That also changed what my x of 1 plus delta x was. Here's x of 1 plus delta x now. That one's no longer valid. And you know something else that's no longer valid? The old value of delta x. This is the new value of delta x right here. So notice what goes hand in hand to taking the end point of the secant and moving it closer to the point of tangency. What goes hand in hand with this is making delta x smaller. Delta x was this big, and then we made delta x this big, and when we made delta x less, that moved the end point of the secant closer to the point of tangency. So moving the end point of the secant closer to the point of tangency and making delta x smaller turn out to be one and the same thing. So let me write down what it is that we just discovered, okay? To get a better approximation, move the end point of the secant closer to the point of tangency. Or equivalently, make delta x smaller. So to get a better approximation, move the end point of the secant closer to the point of tangency, or equivalently, make delta x smaller. Change delta x from being this big to being this big. Make it smaller. So we got a better approximation. So now what can we do to get an even better approximation? And some of us are thinking, well, why not take this end point of the secant and move it even closer to the point of tangency? It worked once. It ought to work again. And that's a good idea. I think I am going to do that. Because it looks like a good idea. I'm going to take the end point of the secant, which was right here, and now I'm going to put it right here. So here's the point, x of 1 plus delta x, f of x of 1 plus delta x. And let me draw the secant. And let me not forget to make this observation also. As I moved the end point of the secant closer to the point of tangency, that resulted in delta x being made even smaller. So this is no longer delta x. Now this is delta x. So to get an even better approximation, move the end point of the secant even closer to the point of tangency. Or equivalently, make delta x even smaller. And look at the secant, look at the tangent. They're not parallel, but they're close. The slope of the secant here is almost exactly the same as the slope of the tangent. They're not equal, but they're not far off from one another either. So these are the right ideas right here. We're thinking properly. Well, sometimes people accuse me of not knowing when to leave well enough alone. And I hope this is not one of those times, but let's push this even further. We want the best approximation to the slope of the tangent that we can get. And we can continue to make the end point of the secant progressively or successively closer to the point of tangency. Well, let's just cut to the chase. Why don't we just move this point so close that it's sitting right on top of the point of tangency? We'll take the end of this secant and we'll put it right down on top of this other point. I mean, can't get any closer than that, right? The only problem with that is if I actually take this end of the secant and move it so close to the point of tangency that the two become one point, that puts us right back where we started, where we only have one point on a line and we need 2 points on a line to compute the slope. So if I take the end point of this secant and put it on top of that point so that they're one and the same point, then these 2 points are one and the same point. We only know the coordinates of one point on the secant, and we can no longer compute the slope of the secant. So we can't actually make this point equal to that point. But I'll tell you what, we would like to make the end point of the secant as close to the point of tangency as possible without the two of these things becoming one and the same point. And in terms of delta x, what are we saying? Well, if we make the end point of the secant as close to the point of tangency as possible, that means we're making delta x as small as possible. And if we're taking the end of the secant and making it as close to the point of tangency without actually becoming equal to the point of tangency, that means that we're taking delta x and we're making it as close to 0 as we can make it without actually making delta x equal to 0. We want to make delta x as close to 0 as we can without actually letting delta x become equal to 0. If we do that, we will be allowing the endpoint of the secant to become as close to the point of tangency as possible without these 2 points actually becoming one and the same point. Now, dig back into the recesses of your mind and see if this seems vaguely familiar. We want to make delta x as close to 0 as possible without actually letting delta x become equal to 0. What process are we describing here? Aren't we describing the process of computing a limit? The limit as delta x approaches 0. If we let delta x approach 0, or if we compute the limit as delta x approaches 0, doesn't that mean that we can make delta x as close to 0 as we want, but at the same time delta x never actually becomes equal to 0? So this is what we want to do. Let delta x approach 0. So the slope of the tangent is approximately equal to the limit as delta x approaches 0 of the slope of the secant. And that means we're computing the limit as delta x goes to 0 of this thing. Remember, this is what the slope of the secant actually was. So that's it. To get the best approximation to the slope of the tangent possible, we compute the limit as delta x goes to 0 of the slope of the secant, which is the limit as delta x goes to 0 of this thing. Oh my goodness. If we compute the limit of the slope of the secant as delta x goes to 0, not only do we get the best approximation to the slope of the tangent possible, we get the slope of the tangent exactly. Oh, when we went to plan B, we thought we were going to have to settle for an approximation. But because we understand limits now, that's not the case. By going to plan B and computing the limit, we can get the slope of the tangent exactly. So we won't say approximately equal here, like we did here. We'll say exactly equal to the limit as delta x goes to 0 of the slope of the secant, which is the limit as delta x goes to 0 of f of x of 1 plus delta x minus f of x all over delta x. So pass the cigars all around and light them up. We are the fathers and mothers of success here. We succeeded in doing what we set out to do, And this is going to be a very important thing for us to be able to do. Finding the slope of the line tangent to the graph of f of x is a very important thing for us to be able to do. And now I'm going to introduce a little bit more terminology. Okay, first of all, what I have in the red box is what was left over from the whiteboard from where we were working before. But I'm going to define something now, the derivative of the function f of x. The derivative of f of x, denoted this way, is defined to be derivative of f of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And we look at this and we say, you know what? This is the same thing as this, except, whoops. Sorry about that. This is the same thing as this, except that here, x of 1 is playing the role that x plays up here. Well, this is the slope of the line tangent to the graph at the point x of 1, f of x of 1. So what's this going to be? If x is playing the role up here that x of 1 plays down here, then I guess this is the slope of the line tangent to the graph of f of x at the point x f of x. Let's make that observation. So the derivative, this thing, is the slope of the tangent to the graph of f of x at the point x f of x. Well, what point x f of x is that? Well, you know what? I can amend this a little bit. And say at any point f of x, any point x f of x on the graph of f of x. So pick a value of x, plug it in here. We got the slope of the tangent to the graph at that point x f of x. And this can be any point on the graph of f of x. Now that's a lot to take in all at once. And we are going to do a bunch of examples so that progressively we can see the full implication of what's being said here. Now I'll make another remark that's not nearly as profound. This thing right here, the derivative of f of x, oftentimes we refer to this thing as f prime of x. So whenever you hear derivative, think f prime of x. And whenever you hear anybody say f prime of x, think derivative. This is a very common expression used to describe the derivative of f of x. More often than not, when people see this, they'll say f prime of x rather than derivative of f of x. So this is just new terminology. The derivative of f of x, we often refer to it as f prime of x. Now, maybe an example or two or three. This is an example that we should do before we actually go to computing a derivative. Just to make sure that when we compute derivatives, there are no other distractions. Given the function f of x equals x squared plus 2x minus 3, compute f evaluated at x plus delta x. Okay, so here's f of x plus delta x. Notice that down here, x plus delta x plays the role that x plays up here in the definition of the function f. So every place that we see an x up here in the definition of the function f, we're going to put x plus delta x down here. See, this is our definition of the function, or our model of the function. Down here, x plus delta x plays the role that x plays up in here, x plays up here in our model of f of x. So every place up here that we see an x in our model, we're going to put x plus delta x down here. Okay, I see an x up here, x squared. I'm going to put x plus delta x down here. X plus delta x squared. See? X plus delta x plays the role down here that x plays up here in our model. Also up here in our model, we have plus 2x. So I'm going to let x plus delta x play the role down here that x plays up here in my model. So where I see an x up here in my model, I will put x plus delta x down here. And up in my model, I also have minus 3. And this has nothing to do with x. So I don't have to worry about letting x plus delta x play the role of x here. There is no x here. So this is f of x plus delta x. And notice, every place I see an x up here in my model, I put an x plus delta x down here. That's exactly how we do this exercise. Now we're going to compute our derivative. Okay, new example. New example. We're working with the same function, but we're doing something different. F of x equals x squared plus 2x minus 3. And our instructions are compute the derivative, f prime of x. Well, how are we going to do that? It turns out we don't have much of a choice. At this point in calculus, we have exactly one tool in our tool bag. We know that the derivative of f of x is defined this way. F of x, the derivative of f of x, or f prime of x, is defined to be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And in the middle of this problem is not the best place to be mentioning this, but I do need to mention it. This is a relationship that we should memorize. This is the definition of derivative. We should remember that the derivative f prime of x is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. This is something that we definitely want to commit to memory. And as bad as my memory is sometimes, even I have this committed to memory. It's just one of those things that if we know calculus, we should know. Okay, well, our goal is to compute the derivative of f of x. We're going to use this definition to do that. And the first thing we have to do, other than declaring our intention to compute the limit, the first thing that we have to do is compute f evaluated at x plus delta x. So, we look at our model f of x, and every place up here in our model that we see an x, we're going to put an x plus delta x down here. So we have an x squared, we're going to put x plus delta x squared down here. We have 2x, we're going to put 2x plus delta x down here. We have a negative 3 here, we're going to put a negative 3 here. So that is our f of x plus delta x. Now we have to subtract f of x, which is this thing. X squared plus 2x minus 3. We're doing great. And last but not least, we put a delta x in the denominator. You know what? I'm just looking ahead a little bit. If I plug in 0 for delta x to compute the limit, this is going to be x squared and this is going to be 2x. So I'm going to have x squared minus x squared is 0. 2x minus 2x is 0. Negative 3 minus a negative 3 is 0. We're going to have 0 on top. We're going to have 0 on the bottom. I need to cancel out a common factor in top and bottom. And that common factor that I need to cancel out is delta x. Before I can do that, I'm going to have to multiply all this junk out and combine terms. So x plus delta x squared. I square the first thing. I square the last thing. And remember, delta x is one symbol. It's not delta times x. Delta x is just one indivisible symbol. So when I put the exponent here, it's the whole thing, delta x squared. So I squared the first thing, I squared the second thing. Now I have to take the first times the second, which is x delta x, and I have to double that. The first times the second doubled. So 2x delta x. Okay. So here's x plus delta x squared. Next, I think I'm going to distribute the 2 inside this set of parentheses. So I'll get 2x plus 2 delta x. And I have minus 3. So I multiplied out my f of x plus delta x. Don't forget f of x. So we subtract f of x, x squared plus 2x minus 3. And let's see what terms fall by the wayside. I have an x squared here, minus an x squared there. I have a 2x here, minus a 2x there. I have a negative 3 here, minus a negative 3 there. Okay, I think that about does it. And notice the terms that got wiped out were exactly those terms that did not have a factor of delta x. All of the terms that did not have a factor of delta x got wiped out. That's not a coincidence. And all of the examples that we'll be doing, that's the way it's going to work out. Notice the surviving terms. This term survived, that term survived, that term survived. They all had a factor of delta x. The terms that have a factor of delta x survive. The terms that don't have a factor of delta x, they're the ones that got wiped out. Now, can I fit this on the same line? I'm going to die trying, I think. Limit as delta x goes to 0. And I have 2x times delta x plus delta x squared plus 2 delta x. All over delta x. I have a factor of delta x in each term of the numerator, so I'm going to factor delta x out of every term. Here's delta x, and I have 2x plus delta x plus 2 all over delta x. And I can cancel the troublemaking factor in top and bottom. I got rid of the troublemakers. I got rid of the factor that was causing division by 0. So now what do? Now I can plug in, right? So I'll denote that. So now I can plug in. And we haven't used delta x before. So I'm going to point something out. In this expression, we have x's and we have delta x's. What is it that's approaching 0? It's delta x, right? So we're going to plug 0 in for delta x. What do we plug in for x? Nothing. We leave x alone. X and delta x are two completely different variables. Delta x is approaching 0, so we plug in 0 for delta x. We plug in 0 for delta x only. There's our answer. And this is a rather odd situation. Up until now, whenever we've computed a limit, we always got a number for an answer. This is the first time that we computed a limit where our answer was actually a function. So let's write our result down. F prime of x equals 2x plus 2. Very good. And we will encapsulate that, showing that this is our answer. Okay, congratulate yourselves. You've just computed your first derivative. And the derivative is a big tool in calculus because the derivative tells us the slope of the line tangent to a function. And remember, that's a major problem in calculus. That's a major thing of interest in calculus, the slope of the line tangent to the graph of the function. Let's take this example and do another example. Okay, new exercise, but we're dealing with the same function. F of x equals x squared plus 2x minus 3. This is the same function whose derivative we computed in the previous example. And the directions say compute the slope of the tangent to the graph of f of x at this point. X f of x equals -1, -4. Okay. The slope of the tangent is f prime of x. And from the previous example, that was 2x plus 2. This tells us the slope of the tangent at any point x f of x on the graph of our function. And I put y here, but maybe just for consistency's sake, let me just continue to say f of x. Now, to get the slope at this point, what do I do with this formula? It's a function of x, isn't it? So what do I actually plug in here for x to get the slope of the tangent when x is equal to -1? Shouldn't we just plug this in? So we would get f prime evaluated at -1. So we're plugging -1 in for x in the derivative. So here we'll plug -1 in for x. Ooh, son of a gun. The slope is 0. The slope is 0. What does that mean? We have a horizontal tangent right at that point. Now, we'll explore that in just a little bit. Notice something odd here. We have a point on the graph -1, -4. And to compute the slope of the tangent, we didn't do anything with the y coordinate. The slope of the tangent was dependent only on the x coordinate. We had to take the x coordinate of the point and plug it into the derivative, and that gave us the slope. The y coordinate of the point turned out to have nothing to do with the slope whatsoever. And typically that's the case. Let's go to this one. We want to know the slope of the tangent at the point x f of x equals 0, -3. So at the point x f of x equals 0, -3, the slope of the tangent is equal to f prime. Well, in our model for f prime is a function of x, right? So what are we going to plug in here? We're going to plug in x. So here, at this point, x is equal to 0. So x equals 0 is exactly what we will plug in here for our derivative. And we're going to get 2x plus 2, where we put x equals 0 in for x. Yes, okay. And that gives us a slope of 2. Okay, very good. And now at the point x f of x equals 1, 0, the slope is going to be the derivative f prime of x. Whoops, except what is x? X is 1 in this case, isn't it? So for x, we're going to plug in 1. And our derivative is 2x plus 2, 2x plus 2, and our x value is 1. So we plug x equal 1 in, and we get 4. Now, the truly amazing thing that this example brings out is that if we compute the derivative of f of x, and that derivative was 2x plus 2, this one formula gives us the slope of the tangent at any point on the original function. All we have to do is plug in the x value of the point, and that gives us the slope. Here the slope was 0. Here the slope was 2. And here the slope was 4. Okay. Maybe we should plot this graph. Maybe we should plot this graph and just confirm our results. Okay, one last example. This example is just a dramatization of the results that we achieved on the previous two examples. We're still working with the same function, x squared equals 2x minus 3. And the instructions are, confirm the results of the previous exercise graphically. Okay, here are the results. At the point -1, -4, the slope is 0. At the point 0, -3, the slope is 2. At the point 1, 0, the slope is 4. That's what our derivative told us in each case. So what about this one? The point -1, -4, the slope is 0. Well, here's the graph of our function. And here's the point -1, -4. And notice that the tangent line to the graph is horizontal. The tangent is horizontal. So the slope of that tangent is what? The slope is 0, right? Excellent. So we confirmed that. Now, from our example, the derivative also told us that at the point 0, -3, the slope should be 2. So I take the point 0, -3 and draw a tangent line to the graph at that point. Okay, now how am I going to compute the slope? I'll pick 2 points on the tangent line. I'll pick this point and I'll pick that point. And going from this point to this point, I go up 1, 2 units, and I go over, let's see, 1 unit. So for this, the slope, let's see, we went up 2 units, we went over 1 unit. So the slope is 2 over 1, or 2, which is exactly what the derivative says the slope of that line should be. And then one more point. At 1, 0, in our previous example, the derivative said the slope is 4. Well, let's see, how are we going to do that now? Okay, we go up, let's see, 1, 2, 3, 4. So we pick a point on the graph here. I'm sorry, pick a point on the tangent here, pick a point on the tangent here, and we go up 1, 2, 3, 4 units, and we go over approximately 1 unit. So slope is equal to 4 units up. Let's see, we go over 1 unit from here to here, and we go up 1, 2, 3, 4 units. So the slope is 4. Exactly what the derivative said we should get for a slope. Now, I think I will give you one homework exercise to do. Yeah, well, I'll just include that with the instructions on Canvas. I'll give you one homework exercise to do, and tomorrow we'll do a few more.